Our first speaker is Aaron Brown from Northwestern University. His title is Lattices Acting on Manifolds.
Okay, so thank you, John. And so thanks to the organizers for putting together this event. It's been a lot of fun. It's my first time in India. And I think special thanks to Sabya and Radhika for doing all the really hard work in the background and making this a really, really fun and really special event. So maybe I'll thank you guys specifically. And so I don't do complex dynamics, and I don't do Teichmuller dynamics, and I don't actually really do homogeneous dynamics. So now I'm wondering what I'm doing up here, but I'm a consumer of homogeneous dynamics. So maybe rather than telling you what I don't do, I'll tell you what I do. So my elevator pitch is I grew up in smooth dynamics and smooth ergodic theory, and try to use the tools from smooth dynamics to say things about group actions. So I'll try to tell you some stories about what I've been thinking about the last 8 or so years in this direction. So I think I'm going to keep a dictionary on the right side of the board here. So groups that I'm interested in today. So I'll start with G, will be SL and R. And I want to impose a higher rank condition. So when n is 2, this is not higher rank. So I'm going to force n to be at least 3. And then gamma will always be a lattice subgroup. So it's a discrete subgroup of G, and it has finite covolume. There are co-compact ones, but if you've never seen a lattice subgroup, you can always just assume gamma is S, L, N, Z, the integer points. And these, well, this certainly exists, and it's a lattice. This is not co-compact, but there also are co-compact lattices, and there's lots of lattices to play with. And what else do I want? I want throughout M will be compact, maybe just connected, so I don't have to say it. Connected, smooth manifold. Manifold. At some points, I'll actually specify what the manifold is, but for now, it can just be whatever. And then what I really want to study is actions of this group on this manifold that are sufficiently smooth. So I'll call my action alpha. It goes from gamma to the diffeomorphism group of M. And so what is an action? It's just a morphism from this discrete group to this gigantic unwieldy group over here. And I'm not specifying the regularity. Maybe for simplicity, I'll just assume these are all C infinity diffeomorphisms. Most everything I say works in C2 or C1 plus, but C infinity is good enough for today. So maybe I'll just leave this here so I don't have to write over and over again. And let me write down a couple of other groups. Well, maybe let me write down first a few motivating questions. So the first question is existence of alpha. So does there even exist a not stupid morphism from gamma to the diffeomorphism group? Another question is just the classification of such things. So if there is a non-silly one, of course, you could just map everything to the identity diffeomorphism. So that would be a silly action. But if you have a non-silly action, can you classify them? Another question is, are there non-trivial perturbations once you have an action? Perturbations. And one other sort of story in this whole, or thing you can ask in this whole story is questions about factor actions, and specifically smooth factors. Okay, so those are all things you could ask, and I'll try to say something about, I'll try to say something about each of those. Maybe one other thing I want to emphasize is some of my favorite subgroups of G. So I'm very bad at linear algebra. So my favorite subgroup of G is the following. A is the diagonal subgroup of the form e to the t1, e to the tn. And I know how to multiply diagonal matrices, so I like this subgroup. I put it in SL, so the determinant is 1, so there's a relation here, which is that t1 plus tn is equal to 0. And so this is an abelian group. I took it connected, and I have one relation. So this is just a copy of Rn minus 1. And I took n to be at least 3, so this is at least 2. So this is a higher rank abelian group. It has rank bigger than 1. And I have another favorite subgroup, which is called P, which will play a role. And it's just all upper triangular matrices. So I have whatever I need on the diagonal to have determinant 1. I have stars up here, and I have zeros here. So this is the upper triangular matrices. Sometimes this would be called the Borel subgroup. And this has the form of A, semi-direct sum n, and here n is nilpotent. So these groups will appear once I start actually trying to say a little bit about how things are proved. And, OK, so before I start telling you stories about what I've done, I think I want to tell you some classical results that are sort of, I don't want to tell you technical things about the proof, but I want to tell you some classical results that motivate how we actually prove things. So let's go back to Furstenberg, and let's look at the map f from S1 to S1. F of x is 3x mod 1. And this is like the first example when I even teach an undergrad dynamics class. We study this maybe after we did circle rotations. We do expanding maps. And here's facts. So for any 0 less than, I'm going to reuse alpha here, less than 1, there is, there's a transitive f invariant lambda. So there's a non-trivial, dynamically non-trivial, but lambda is closed and invariant with Hausdorff dimension. Maybe I'll write it like this. Hausdorff dimension of this set equal to alpha. So you can find lots of exotic closed invariant sets. Anything you want between 0 and 1. 1 would be everything. 0 might be periodic points, but you can find lots of Cantor sets in between of arbitrary Hausdorff dimension. And you can also find ergodic F invariant Borel probability measures with, again, there's a notion of Hausdorff dimension of a measure. The measure is equal to alpha. But if you don't like Hausdorff dimension of a measure, you could also calculate its entropy. And here, I took an affine map, so its Lyapunov exponent is just log 3. And here, the entropy is alpha log 3. So you can find exotic closed invariant sets, and you can find exotic Borel probability measures. And here's the theorem of Furstenberg. Which is, instead of just looking at a single map, you look at another map that commutes with it. So you let G, also from the circle to itself, be G of x is 2x mod 1, or anything else that commutes and is, what do you want? You want to say rationally independent. So 2 and 3, I think, are rationally independent, or their logs are rationally independent. So then, the only closed F and G invariant set lambda in the circle is either 1, finite, or 2, everything. So suddenly, once you have some commuting dynamics, or Another way of thinking about this is once you have some non-trivial symmetries, so things that commute, sometimes we think of those as symmetries of the original F. You can't have exotic closed invariant sets. And then Furstenberg asked the measure question. I don't know if he actually made a conjecture, but he asked the question. And the best result is due to Rudolph. And sort of building on work of Russ Lyons and Amy Johnson. It has the analog for measures, except that it's a little bit hard to understand the zero-dimensional measures. So let's let mu be ergodic and F and G invariant. And so it's ergodic for the n squared semigroup generated by these. So it might not be F ergodic or G ergodic, but it's ergodic for the semigroup action. And it's invariant by both. Then either, well, there's an obvious invariant measure, which is mu is Lebesgue, or 2. What you'd like to say is that mu sits on a finite orbit, sits on a periodic point, and nobody knows quite how to prove this. But what you can say is that the dimension of mu is equal to 0, or alternatively, the entropy of any of the generators or anybody in the semigroup is equal to 0. So it's this second theorem and various generalizations of it that's going to actually underlie the proofs of the main results I'll talk about. And so I won't go into the details, but if you know a little bit about this theorem, maybe you can sort of believe the proofs when I try to wave my hands at them. And sort of the fundamental principle here is that if you have some large group acting, whatever large means, on M, with an invariant measure, an invariant probability measure. Maybe I'll call the measure mu. And then plus, and then you always have to, you have to assume something, some technical criterion. So I'll just put some various technical criterion in parentheses. Maybe you want some sort of transversality, or you want some irreducibility, whatever that means. Or you put some assumptions on the Lyapunov exponents. Lyapunov exponents, or sometimes you put some entropy assumptions and various versions of these. So I'm not going to be precise about what any of these things mean, but you need some assumptions. But this should imply that the Hausdorff dimension of mu, rather than what happens for a single hyperbolic map where it can sort of be all sorts of numbers, it could be fractal, is that it's integral. And mu is, it might not necessarily be ambiently homogeneous, but it's at least homogeneous along stable and unstable manifolds. So I'll just write stable manifolds. So this is a principle. Of course, it's nothing precise here, but this has been invoked in a lot of places, especially in homogeneous dynamics. So, well, first starting with abelian groups on the circle, and then abelian groups on the torus, and then you can look at abelian groups acting hyperbolically on nil manifolds. You could also look at the diagonal flow on G mod gamma and study things like quantum unique ergodicity or Littlewood's conjecture. And this principle has been worked out in those homogeneous settings where you have a higher rank abelian group that's sufficiently large. You have some invariant measure. You have some technical assumptions that allow you to run some machinery. And then you are able to show this measure has to be homogeneous in some sense, or at least homogeneous in some directions. And that's enough to prove a lot of theorems. So this is what's underlying most everything that I'll talk about today. OK. So I spent 15 minutes waving my hands at something. Now I'll try to say something precise. But please interrupt if there's questions at any time. So maybe you'd ask, why would you even care about these kinds of groups, these kinds of gammas? And there's a lot of classical results saying these things are very rigid with respect to linear representations. And I'll just write down sort of the best result in this direction, which is Margulis superrigidity. So this is a theorem without, I'll probably put a lot of quotes. This is a version of Margulis superrigidity. And again, I'm saying a special case. There holds in lots of more generality. But for a higher rank lattice gamma, every linear representation from gamma to a linear group, so a finite dimensional linear group, say GLDR, is classified by, so there's a few things that can go into this. So you can put the restriction of an ambient representation into, and this thing has determinant 1, so this also has determinant 1. So you can restrict an ambient representation to gamma. And then there's a few other things you can do. You can do sort of Galois conjugation. And you can also do, there's all sorts of finite index noise. And so basically, every linear representation is completely classified by a representation of the ambient group plus some algebraic nonsense. And this is superrigidity combined with the arithmeticity theorem. And so just a corollary of this, which is not completely clear that it's a corollary, but it is, the way I've written it, is that every representation, rho from gamma into GLDR, I'm going to leave a space if the dimension of the target representation is strictly less than n. There's no room for there to be an ambient representation. And the Galois conjugate, there's actually no room to do that as well. And so this satisfies, so this has finite representation, a finite image. So rho of gamma is finite. And so if the dimension of the target space is too small, you just can't have any interesting linear representations. So starting in about 2016, I started a project with David Fisher, who unfortunately decided for various reasons he couldn't come for this week, and Sebastian Hurtado. So me with David Fisher and Sebastian Hurtado. So people had been very interested in the analog of this question, where you replace a linear group with a diffeomorphism group, because that's the world of actions. And we were able to show the following. And again, I won't restate the hypotheses. So these are my standing hypotheses on the groups. So suppose that the dimension of M is strictly less than n minus 1. And after this, I'll talk about what happens in dimension n minus 1. Then for any action, so any morphism from such a gamma into the diffeomorphism group, and here I'll even emphasize we can do this in low regularity, so C2 is good. So there just aren't very many actions. So this has finite image. So the image, the range of the representation, the range of the action is just finite. So it's just acting by some finite symmetries of the manifold M. Maybe it's acting by the trivial map. What is n? So n is always the n inside of G. Yeah. And gamma is a lattice in SLNR. And of course, you can ask what happens if you replace this with a different higher rank Lie group, and if you want to go through all those combinatorial numerology, I'm happy to do that afterwards, but I'll just say things for SL today. So there's aren't any actions on these manifolds. And so I won't say much about the proof, but I'll just say I'll just write down a handful of ingredients. So we first proved it for co-compact lattices, and then worked very hard for non-uniform lattices. Some of the ingredients that go inside are Laforgue's strong property T. Another key ingredient is machinery and smooth dynamics, in particular, a lot of work about Lyapunov exponents. And a little bit of ideas about metric entropy are sort of hiding in the background. It's not clear where they're at all playing here, but. And in the case of non-uniform lattices, we really have to use dynamics on G mod gamma. And again, I've never proved a theorem about dynamics on G mod gamma, but I've used lots of theorems. And so in particular, we use quantitative non-divergence and exponential mixing, various quantitative non-divergence of unipotent orbits and exponential mixing on G mod gamma. It's not even clear where G mod gamma is coming into play on the statement of the theorem here. And just the quantitative non-divergence of unipotent orbits, that's the quantitative version of observation that goes back to Professor Dani of the non-divergence with Margulis, the non-divergence of unipotent orbits. OK, so in dimension n-1, there's just not a lot to study. So the reasonable question to ask is, what can you say in this first dimension? And why is this the reasonable threshold to put in here? And there's an obvious action in dimension n-1. So SL n R acts on Rn, and it acts linearly. And so it induces an action on the space of lines or the space of rays. And so this induces any subgroup of this is going to act naturally on the space of rays, or Rp n-1, the space of lines. And that's the natural action in dimension n-1. And so to make this, one version of making this precise is, let's look at Sn-1 as unit vectors. And then we can say alpha of gamma of a unit vector is just act linearly on it. So gamma hit x, but it's no longer a unit vector. And so you renormalize. And that's what the projective action is in some coordinates. And so here's a nice action to look at. And I think I'd like to generalize this a little bit. So instead of acting on rays, and really we shouldn't look on rays, we should projectivize. So acting on lines, you could look on subspaces. So you also have a natural action on Grassmannian of k-planes in Rn. And this has very similar properties to the action on lines, the action on planes. And if you like, you can even do gamma acting on flag varieties in Rn. And maybe I'll just write a little bit about what is a flag variety. But I'll take my eraser with me. So, well, I don't know what the standard notation is, so I just made something up. So I'll let sigma be a set of integers. So it's I1, which is bigger than 0, less than I2, less than IL, which is less than n. And then what is a flag given by this combinatorics? So it's 0 is a is an element of V1, is a subset of V2, is a subset of VL, is a subset of Rn, and the dimension of Vi, or maybe Vj, is Ij. So the first one has dimension I1, the second one has dimension I2, the last one has dimension IL, and they're all proper inclusions by dimension constraints. And so this is a flag, and then maybe fancy F sub sigma. This is the space of all flags. With this fixed combinatorics, and you have a natural projective action on this object. And I'll just show one other way of thinking about this space, which also is another way of thinking about just Rpn minus 1, which is that S, L, N, R, this acts transitively on the space of all flags. So flag variety with fixed combinatorics is a homogeneous quotient of this. And so the stabilizer of a flag is, I'll call it Q, is a parabolic subgroup. This is a definition of a parabolic subgroup, if you like, is a parabolic subgroup, which is called Q. And what's another definition of a parabolic subgroup is just that it contains the upper triangular matrices. So i.e., P is a subgroup of Q, which is a subgroup of G. And so if you want to look at Rpn minus 1, then maybe you look at the stabilizer of a flag with one-dimensional subspace in it. So the stabilizer of E1 is either this or it's transposed, depending on which side you're acting on. It's this subgroup with zeros here. And so then Rpn minus 1, it's just G. And here, for strange reasons, I'm going to take my quotient on the left here. So Rpn minus 1, it's of this form. It's SLNR mod this subgroup. Maybe it's transposed because I'm not sure which side I'm taking the quotient on. And then every flag manifold is also of this form. It's G mod Q, not the rationals, a different Q. Q sigma, where Q sigma is just some subgroup containing the upper triangular group. And gamma acts on any flag manifold or flag variety by, and there are just bookkeeping reasons in my head that I'm taking the quotient this way. So gamma of QG, just to make it make sense, I'm going to make it a right action. So it should be QG gamma inverse. And so this action on unit vectors, or the natural action on spheres, it just completely generalizes to actions on flag varieties. And I don't know if I'll actually say anything about this, but if you look at the natural, so these things are complete projective varieties. This is a projective action. So the gamma action on a flag variety has some properties, has no gamma invariant Borel probability measure. This is a fact you can prove. If you know what proximal means, you know how to prove this. And it also has zero topological entropy. So the topological entropy of every acting element is 0 for all gamma in gamma. Okay, so I told you one theorem, which is about there never are some examples, and then I showed you some examples of projective actions. And now I'll try to tell you some theorems, but maybe other questions. So in dimension n minus 1, you could ask what kind of actions exist. Theorem. And this is, we announced this a long time ago and kind of realized that the tools to prove this theorem prove a lot of other theorems, which is why the paper still doesn't exist, but it's very, very close to being on archive. But we use the same, once you find a hammer and then the world is full of nails, and you want to hit every single nail that you can find. So this is due to myself, Federico Rodriguez Hertz, and Jiren Wang. I'm tempted to say Z Wang, but then there's also too many Z Wangs. So this is Jiren Wang, and this is Federico. There's also other Rodriguez Hertzes. So suppose that M is compact connected, and its dimension is n minus 1. So the first dimension that we have at least some action to play with. And suppose I have an action of one of these groups gamma by diffeomorphisms. And again, 1 plus holder works here. If you like C2, I'll actually put CR on M. And so here R is strictly bigger than 1. And of course, this could be an action just by the identity map, so that would be silly to study. And so let's have it be with infinite image. So it's not an action by finite symmetries or by, by just the identity. So what can you say? And again, sort of when you unpack things or maybe repackage things, there is a measure hiding somewhere. And this measure is invariant under a higher rank abelian group. And you can upgrade its regularity and then prove the following theorem. Then there is a CR diffeo. Let's call it H. It goes from M to Sn minus 1 or Rpn minus 1. So really the right thing to say is that there's a CR covering map to the projective action. So just because immediately once we know that there's an infinite action on this space, we already have the topology. And such that for all x in M and all gamma in gamma prime, which has index 2 inside of gamma, and there's just a silly index 2 flipping that you can do that makes the next thing I'm going to say not quite true if you do the whole gamma. But if you restrict to an index 2 subgroup, what I'll say is true, such that if I take my mystery action and do gamma to it and apply it to x, and then do my change of coordinates, that's the same thing as doing the standard projective action times my change of coordinates to x. And so here, this is the standard projective action on the space of rays or the space of lines. So up to as regular as the action change of coordinates, you know what the manifold is, you know its topology completely, and you know what the action is, at least up to index 2, you know exactly what the action is. It had to be the example I wrote down before. And so here's a global classification. In this first dimension, where you have non-trivial actions, the only actions are the ones I wrote down up to an index 2 fiddling around. John?
So there's no Galois conjugation issue arising here?
Not here because the complexification of SL is SU, and SU is much bigger than SO. And so it can't act by isometries. It can't fit into an isometry group. If you do the complex version of it, then that arises. If you replace R with C, then there's another case here. Yes?
Does it already know that there were actions on exotic spheres?
I don't know. So this is the standard sphere. That's a good point. And the standard projective space is not an exotic sphere. I don't know that there's anything about saying that they can't act on an exotic sphere. But yeah, it is the standard smooth structure here. And really, we build a map, just to emphasize, we really build a map from H, from M to G mod Q, where Q is the appropriate parabolic, which is gamma equivariant. And so we really are getting the smooth structure coming from the G mod Q. That's how we build this. We build a covering map this way. And so since I spent some time just at least waving my hands at what a flag manifold is, let me tell you a theorem about these as well. So again, the tool we developed to prove this theorem is really about classification of invariant measures, and it ends up being and I haven't even told you where the invariant measures live, but it's some hammer that then we found lots of nails. Like, you know, in springtime, your deck, all the nails have popped out over the winter, so we found lots of nails to hit. So here's another theorem. Again, with myself, Federico, and Jiren. So let's let maybe alpha naught from gamma, and maybe I'll write it like this, to a flag manifold, be the standard projective action. So it's just the gamma action on a G mod Q, where you pick the appropriate Q that stabilizes a representative flag. And so then, for any action of the same group to the diffeomorphism group, and here I'll just put infinity just to be careful, of the flag manifold that is sufficiently C1 close to alpha naught. So I haven't finished my sentence yet, but this is a finitely generated group. So you can talk about the C1 topology on group actions by looking at what it does on generators and asking that the C1 distance be close on a generating set. So it makes sense to ask if this action is C1 close to this guy. And so this is asking about what kind of perturbations do there exist, or what kind of perturbations exist of these standard actions. And so what we prove is that every action that's sufficiently C1 close is of the original guy up to an obvious equivalence. So then for anyone that's sufficiently C1 close, there is a H from the flag manifold to itself, which is as smooth as the action. So here it's C infinity, diffeo, which conjugates the two actions. So H precomposed with mystery action is our model action precomposed with our coordinate change, and this is true for all gamma in gamma. And so this is what's called a local rigidity result. We start with a model algebraic action. Here it's a projective action on a standard projective object. If you don't like the flag manifold, you can put the Grossmannians here, so the action on Grossmannians. If you perturb the action of any lattice up to a coordinate change, a smooth coordinate change is the original action. And the statement of this isn't so new. So for co-compact gamma, this is an old result due to Kanai in some cases. And then the most general result is old paper of Katak and Spazier. But what I'd like to emphasize is that we don't use co-compactness of the gamma at all. So in particular, this holds for SLNZ, because somehow we're using very different machinery. And I'll also just say, can compare to C0 local rigidity of the same kind of boundary or projective actions for co-compact gamma. And this is a recent paper of, let's see, Connell. I think there's 2 N's in Chris's name and 2 L's. Mitul Islam, Tang Nguyen, and Ralph Spazier. So for the co-compact, this is early 90s, but whatever machinery we're developing does the non-uniform case at the same time. So it really is some sort of new hammer. Okay, so I have 20 minutes left, and yes? So I'm assuming the action is C infinity. I'm assuming it's a C1 small perturbation. But the conjugacy, if you like, this is R, and this is R, and then the R needs to be bigger than some R of G. There's some lower threshold, but it only needs to be a C1 small perturbation. That's. I think I'll just, rather than formulating another theorem, I'll put a remark here, which is that we can also prove smooth factor theorems. Again, for projective actions on flag varieties or generalized boundaries or whatever these things are called. So I won't write anything down. I'll just say out loud. We heard about Margulis's normal subgroup theorem. The standard proof studies measurable factors of these kinds of actions and shows that all the measurable factors are measurably isomorphic to things of this form. They are also, all the measurable factors of an action on a flag variety is a different action on a flag variety. And Professor Dani extended this to continuous factors. So if you have a surjection between gamma equivariant maps, one of the maps is an action on a flag variety, then the factor is also naturally an action on a flag variety. And when you have a smooth factor, we upgrade the map to be a smooth, to say that they're smoothly natural or they're smoothly equivalent. But I won't formulate that. So I'll maybe take 5 minutes just to sort of, I try to convince you that invariant measures are important. I try to convince you that the group A and the group P are important. But so far, the group A and the group P haven't appeared, and no measures have appeared. So let me just try to tell you the context where our hammer lives. So we have gamma acting by diffeomorphisms of a manifold M. And gamma is a lattice in G. And so what we're going to do is, instead of looking at gamma acting on something, we're going to look at G acting on something else. And this is a standard construction, but I'll write it down for you. So you look at G times M, and you let gamma act on the right, and you let G act on the left. And what are these actions? So G comma X hit on the left by H is just translate in the first coordinate and do nothing in the second coordinate, which looks almost stupid until you remember that there's a right action as well. G comma X hit on the right by gamma is G gamma. And then this is supposed to be a right action, so I have to twist by the inverse alpha gamma inverse of X. And right actions and left actions commute. So then you build something that in all of our papers we call M superscript alpha. It's G times M modded by this right gamma action. And because we mod by the right gamma action, the G action actually does non-trivial things in the second coordinate, because when we pass a fundamental domain, we're actually doing this as some monodromy. We're doing this action as a monodromy. This has a G action on it because the left and right actions commute. And this fibers over G mod gamma in a G equivariant way. And so we have this structure of a fiber bundle. So the fibers of M alpha they're diffeomorphic to M. And we have a G equivariant fibration. And alpha is sort of the monodromy of the bundle, meaning that when you leave a fundamental domain downstairs, when you want to come back, you're actually just coming back by this map. And so here's some way of sort of coupling this mystery action with everything we know about homogeneous dynamics on G mod gamma. In particular, we know about diagonal actions down here. We know about unipotent actions, and I can be a consumer of everything about homogeneous dynamics in this space to try to prove things about nonlinear dynamics in this space. And now P is my favorite subgroup. It's my second favorite subgroup. It's the group of upper triangular matrices. So it has the diagonal, and it has all the upper off-diagonal terms. And this is what is it called? It's abelian by nilpotent, so it's solvable, and so it's amenable. This is amenable. And so G is definitely non-amenable. G might not have any G invariant measures on this bundle. There's G invariant measures down here because it's the Haar measure. But there might not be any G measures here, but there definitely are P measures because P is amenable. And so what we do is we study the P, we study ergodic P invariant probability measures, mu, on M alpha. And if I have P acting on M alpha and a mystery measure here, P also acts downstairs. And there's a unique P measure downstairs. It's the normalized Haar measure on a fundamental domain. So this projects to the Haar measure. And so all these measures upstairs, we know what the marginal is. We know it's the Haar measure. And again, the dynamics on G mod gamma with the Haar measure has been studied for centuries, I don't know, maybe decades, but we can use all the tools down here to try to say things about what's happening here. And the idea is that, well, P has an A inside of it. A is higher rank, Rn minus 1. It sits inside of the P. And whatever principle I wrote down at the beginning, we can try to show that mu is in some sense homogeneous. And the way you prove all of these theorems is you show that actually mu, the measure that exists because it's an amenable group acting on a space, actually is the graph of the conjugacy you're trying to build. So there's some unpacking to show that mu really is the graph of the conjugacy. And I'm not going to try to unpack whatever these two sentences mean, but morally, this is what we do. We can upgrade a mystery measure to being, well, first it has integral dimension, and then it's homogeneous in a lot of directions, and then we can piece these homogeneity together to actually have it just be a measure sitting on the graph of the conjugacy we're trying to build. Okay, and now I have probably 11 minutes. So maybe this is a good place. I'll pause to see if there's questions.
So,
Yes?
you're using the classification of diagonal ergodic measures?
Nope, because I'm just using P. So the classification of P measures is very easy, because there's only one. I'm not using the A downstairs. I'm using the A upstairs, but I'm starting with a P measure.
So you're using something from homogeneous dynamics here?
I am, along the way, using some tools about homogeneous dynamics in the base. So, we are using, especially when we show the work with David and Sebastian, we study this bundle and we use quantitative non-divergence of unipotent orbits down here. When we are studying the action up here, we need to use the non-divergence of unipotence down here. And when we're studying the dynamics on this bundle, we also use exponential mixing of diagonal flows down here. And so we are using a lot of the homogeneous dynamics in the base to sort of couple something that we know a lot about with some mystery object. Yes?
Generic orbit downstairs, and you look at the induced bundle of that. Are there some Lyapunov exponents that you get, or at tangent space level?
Yes. And so what is hiding behind all of this is earlier work about studying A measures on this bundle that project to the Haar measure. And okay, well, so let me say one technical thing. So now we can look at A acting on M alpha with mu. And this is projecting to G mod gamma with Haar. So we're just going to restrict to the A action. And now we can look at lambda 1, lambda IF. These are the fiber-wise Lyapunov exponents for the A action on this bundle with respect to this measure. So there's a fiber pi, and we can look at the F, which is pi inverse. We can restrict the derivative of this action, this is at least C1, to the vertical fiber here, and we can study the Lyapunov exponents. And Lyapunov exponents of an abelian group action, they are linear functionals to R. And, but there's another bunch of linear functionals on the diagonal group, which are the roots of this Lie algebra. And so we also have beta from A to R. Maybe I'm being sloppy in identifying this guy with its Lie algebra under the exponential map. These are the roots of G. And here I made sure that this projects to the Haar measure, so the next thing I'm going to say is correct. And I probably ran out of space. So. And so here's a proposition. Suppose I pick a root, beta is a root such that beta is not positively proportional to any of my fiber exponents. So this is not of this form, where C is positive and lambda IF is any fiber Lyapunov exponent. So just as linear functionals, I'm going to assume that this is not positively proportional to this guy. Then this mystery measure, which is on this bundle, is U beta invariant. It's invariant under the unipotent subgroup parameterized by this beta. And so, okay, I wasn't planning to say anything about this, but we started with just a P measure on this bundle. But actually, if M is very low dimensional, it has to be invariant under a lot of things that are outside of P. It has to be invariant under a lot of the root groups that, because there's only the dimension of M possible fiber exponents, because each of them comes with a one-dimensional, at least one-dimensional object. So there's an upper bound on the number of exponents, so there's an upper bound on the number of roots that could be positively proportional to something. So you get a lot of extra invariance when the dimension of the fiber is small. And so this is also hiding in the background of all these theorems. Okay, so there's 5 minutes left, and so I want to just allude to something that something that I'm also working on with a postdoc of mine, which it's in this same story, and I really like it. And so now let's just go to the dimension of M is equal to N. And there are two stories I could tell here. and I will only tell one of them, but I'll write down what they are. So the first story is we could study volume preserving actions by gamma on M. And this one I won't say anything about, but I can say things about this if you'd like to know. But now I'll just try to say something really cute, but that takes a lot of work to show. We could study actions of these kinds of groups on N manifolds with positive topological entropy. And for which gamma, for some, and maybe you'd like to say lots of gamma in gamma. So in dimension n-1, the model action, and what we show is that every action is projective. Projective actions, every element acts with zero entropy. A generic element will be more small, and other elements will be variations of more small, so they can't have any entropy. And here's another name that I have to give the first name to. So this is due to me and postdoc at Northwestern. So this is Ho-Min Lee. There's too many mathematicians named Lee. So and so the same setup. So suppose that the dimension of M is equal to n, and alpha is an action of gamma by diffeomorphisms. Here, the magic word we're going to use is Yamden-Newhouse. And if you know what Yamden-Newhouse means, it's some upper semi-continuity of topological entropy. This is going to require, we work in the C-infinity category. I won't say where we use it, but it's used in the proof. So suppose this is a C-infinity action with one element acting with positive topological entropy. And of course, then all of its conjugates do, but really all we need is just one element. So what can you say? So then, one, there exists a gamma invariant, absolutely continuous probability measure. Where did this come from? I know the proof, but it's not anywhere in the hypotheses. Gamma is very non-amenable, so there's not even a reason that it has any invariant measure. But in this case, we're able to show that there actually has to be a gamma invariant, absolutely continuous measure for this thing. Two, we're able to show the following. So I didn't make any assumptions about which gamma this is. All I assume that gamma is a subgroup of SLNR. And abstractly, gamma is abstractly commensurable with SLNZ. Up to conjugacy and finite index, it has to be the integer points. And so in particular, I can't have a co-compact lattice act in dimension n with any element having positive entropy. And then three, and here we may need an extra hypothesis, so we might need n at least 4 just for some things that arise in the proof, is that M is sort of measurably a torus, and the action is measurably conjugate to the natural affine action of this on the Tn on the torus or an infratorus. So measurably, the model in dimension n is SLNZ acting on the torus, and up to some measurable change of coordinates, that's the only thing that can happen. And that's for showing the measurable conjugacy. That's how you prove that the acting group actually has to be SLNZ. Okay, so I think I'm officially out of time. So thanks for listening to me. Sorry there was no complex dynamics. There was a little bit of homogeneous dynamics, no technical dynamics, but hopefully it was still enjoyable.